Today, we're exploring systems of linear inequalities in one variable. This is an important topic that lets us handle multiple conditions at once. In this lesson, we'll see how to solve systems of inequalities that involve just one variable, like x, but with more than one inequality. Let's remember what we mean by a system of inequalities. When we have multiple inequalities involving the same variable, like x, we're looking for values of x that satisfy all of the inequalities at the same time. This combined solution set gives us a range, or sometimes even specific values, that work for the entire system. In a system of linear inequalities in one variable, we'll typically follow these steps. Graph each inequality on a number line. For each inequality, we'll first plot it on a number line. This helps us see the range of values that work for each inequality individually. Remember that for inequalities like less than or greater than, we'll use an open circle to show that the boundary point is not included. For less than or equal to or greater than or equal to, we'll use a closed circle to include the boundary point. Identify the intersection of solution sets. Once each inequality is graphed, we focus on the overlapping region, or intersection, where both inequalities are true at the same time. This region is our solution to the system, as it shows the values that satisfy all the inequalities. Interpret the final solution. Our last step is to describe the solution set. We'll write this as an inequality or interval that represents the overlapping region. This final solution shows the range of values that meet all the conditions given by the inequalities. By following these steps, you'll be able to break down systems of linear inequalities in one variable into clear parts and easily find solutions. Let's get some practice with examples to see how these steps come together. Solve the system of inequalities and represent the solution on a number line. First, we'll start by graphing each inequality individually on a number line. This will help us see the range of values that satisfy each condition. For the inequality x greater than 2, we'll use an open circle at 2, since values greater than 2 are included, but 2 itself is not. Then, we'll shade to the right to represent all values greater than 2. For x less than or equal to 5, we'll place a closed circle at 5 to include the boundary point and shade to the left to represent all values less than or equal to 5. Now that both inequalities are graphed, we need to find the overlapping region where both inequalities are true at the same time. This overlapping region represents the values of x that satisfy both conditions. In this case, the solution to the system is the range of values between 2 and 5, where 2 is not included, but 5 is. We can represent the solution to this system as an inequality. This inequality shows that x is greater than 2 and less than or equal to 5, which meets both conditions of our system. Now that you've seen how this works in a simple case, let's try a more challenging example. Solve the system of inequalities and represent the solution on a number line. As before, we'll start by graphing each inequality individually on a number line. This lets us see the range of values for each inequality one by one. For x greater than or equal to -1, we'll use a closed circle at -1 to show that -1 is included, then shade to the right to represent values greater than or equal to -1. For x less than 4, we'll place an open circle at 4, since 4 itself is not included in the solution. Then we'll shade to the left, representing all values less than 4. Finally, we need to ensure that x not equal to 2 is represented. This means that we should exclude the point 2 from the solution by placing an open circle at x equals 2 without shading over it. Now that each inequality is graphed, let's find the overlapping region where all three conditions are satisfied. The solution set is where the shading for x greater than or equal to -1 and x less than 4 overlaps, but we need to exclude x equals 2. So, our final solution will be all values from -1 up to, but not including, 4, while skipping the value 2. Now, we can represent the solution to this system of inequalities. This inequality shows that x can take any value from -1 to 4, excluding 2. Nice work! You've solved a more complex system with an additional condition. Next up, let's look at a problem that will put all these ideas into practice. A theater has certain seating restrictions for safety purposes. The number of seats available, represented by x, must meet the following conditions. The theater must have at least 50 seats available, it can have fewer than 200 seats available, and it can't have 120 seats. Which of the following represents the range of values that x can take? To start, let's write each condition as an inequality. At least 50 seats. This tells us x must be at least 50, which means x greater than or equal to 50. Fewer than 200 seats. This condition means x must be less than 200, so we can write this as x less than 200. Not exactly 120 seats. This restriction tells us x not equal to 120, meaning 120 is not part of the solution. So, we have our system of inequalities. Now, let's interpret each condition individually on a number line. X greater than or equal to 50. We represent this by placing a closed circle at 50, including 50 in our solution, and shading to the right. X less than 200. For this condition, we place an open circle at 200, excluding it from our solution, and shade to the left. X not equal to 120. Finally, we represent this by placing an open circle at 120 to show that it's excluded from our solution set. Now that each condition is graphed, we need to find the overlapping region where all conditions are satisfied simultaneously. The overlapping region starts at 50, inclusive, and goes up to, but does not include, 200, while also excluding 120. So, our solution is the range from 50 to 200, excluding 120. We can represent the solution as an interval. Taking into account that we need to exclude 120 from the range, we can write the solution explicitly. This notation shows that the values of x range from 50 up to, but not including, 120, and then from just above 120 up to 200, also not including 200. Comparing this to our options, we see that option B is the correct answer. Great job today! Let's recap the main ideas we covered about systems of linear inequalities in one variable. A system of inequalities involves multiple conditions on the same variable. Our goal is to find values that satisfy all conditions simultaneously. This is often represented as an overlapping region on a number line. We start by graphing each inequality individually on a number line, using open or closed circles to indicate whether boundaries are included. The intersection of the shaded regions represents the values that satisfy all inequalities. This overlapping region is our solution. Finally, we express the solution as a combined inequality or an interval notation, which captures the complete range of values. Be sure to check for any values that are explicitly excluded from the solution, and always verify each condition against the solution set. With these steps, you're well equipped to solve any system of linear inequalities in one variable. Practice makes perfect, so keep challenging yourself with similar problems. See you next time.